Hello all. So in this lecture we are going to discuss about data management in GIS. In previous lectures we discussed about how to represent geographic features. We will have a quick review and we will continue how to manage geographic data in GIS. To describe geographical features we normally apply two types of data. One is spatial data and one is attribute data. And you know that spatial data describes the location and attribute data which specifies characteristics of that location. And these geographic features can be prepared as layers, and these layers can be prepared using two broad data models. One is vector data model, another one is raster data model. And using appropriate data properties, including map projection, scale, accuracy, and what kind of resolution you want to represent. And you can apply these two models and you can represent the geographic features. So how can utilize these geographic features or these layers into day-to-day applications or common computer application system? So that we will discuss while discussing the database management system. If you take the functional components of data management, there are different types of geographic information, and those informations are categorized into two broad data types. And these data types are spatial and attribute data being captured, and while capturing need to ensure the errors and accuracy of the data, and we have to store it in an appropriate environment, and we have to check its integrity, and we have to present or apply this database for various applications. While apply or sharing the database, we have to ensure the metadata of the data. So these are all the broad functional components of data management, and one by one we will discuss through this lecture. I hope you are aware about the two broader spatial data types. One is continuous and another one is discrete. We discussed in last lecture as well. So where the continuous data normally used to represent continuous geographic information such as elevation, rainfall, ocean salinity, and so on. And if you have man-made features, or if you want to represent the future in a discrete manner, we can use the entities like point, line, or areas using both approaches, either vector model and raster model. This raster model is good for continuous data representation, but for discrete, vector is better. But still, raster can be used for both the model or both the data type, both continuous and discrete. The same information we can understand in another perspective, or we call it as a data management perspective, that once we store the discrete information in the database, that we call it as objects, and if you want to represent or if you want to analysis some continuous data, then we use technically called field approach or field data. So the real world entity can be represented either using object approach or a field approach. Of course, the object approach is similar to discrete approach, where you can categorize the geographic data into points, lines, and area, and capture as an object in a layer, and you can represent it. And most of the case you will have a multi-representation depend upon the scale involved in this representation, where point may be represented as area or line may be represented as area, depend upon the scale of the map. If you have a data that has the properties of continuous over space, then which can be represent using a raster approach, because raster is good. Without any gap, the entire area can be represented using raster pixels. So normally the raster is used to represent field information like this. But of course, even with the help of thin triangulated irregular network, we can use yeah, similar to vector approach also to represent continuous data, where each and every location will have some value. So the data in terms of technical aspect can be presented using an object approach or field approach. And of course, there is a chances of converting from one approach to another approach. It's depend on the purpose and how we want to represent the geographic data. Say for example, I have a data of categorical or like integer variable. Say here all cons are represented 111. Either I can use the field approach where continuously I can represent 111, or I can group these similar values together and form an object, and I can represent this as an object as well. So likewise here, the elevations are represented continuously from lower value to higher values using different shades. But the same field information can be categorized into classes using intervals, and you can represent each as separate object, and you can do analysis or do management, etc. So the real world information, continuous information, can also be converted into objects using vector. You can represent it, or even using raster, you can categorize into classes and you can represent it. So it's our responsibility to decide what kind of approach we will employ to represent the real world geographic data. So once the spatial data is decided and designed to represent the geographical information, then we have to think it of what kind of attributes we can add with the spatial data. Based on the properties of data, we can categorize our attribute data into two groups. One is called categorical attribute data, another one is called numerical attribute data. If you have attributes like name or like a place or ranks or some order or some pin code or zip code or some other like codes, then we can represent it as categorical data. And if you have information that represents some like numerical values, then it can be represented or it can be presented as interval data or ratio data, depend upon the data. Say for example, if the data is of relative and don't have natural zero, such as temperature, and you can store it or represent it as interval data. And if the data is absolute and have a natural zero, you can represent it as ratio data, for example, rainfall or age. And these interval and ratio data can be represented as a whole number called integer or decimal fraction called float. And keep in mind the attributes table can also hold spatial information, which means locational information such as name of the state or name of county or name of like places, or a numerical information, say for example XY coordinates. So the spatial information can also be represented using categorical and numerical approach depend upon the data you have. And of course, in order to visualize those spatial information, you must convert those data into shapes using approach of raster model or vector model, and you can display it as map. The next component, functional component of data management is data capturing. So we will start with the spatial data capturing, and we will go ahead with the attribute attach with the spatial data. The spatial data can be captured using methods like digitization. You can digitize the manual maps, or you can use the instrument like scanners, where you can scan the analog data and you can convert it into digital. So if you are digitizing using digitizer tablets or desktop method, screening digitizing method, or some other digitization method, you will directly convert the analog information or raster information into vector. At the same time, you can also do some automatic process where you can scan the maps, scan the data, and you can do data conversion, automated data conversion called the vectorization, where the scanned image by using some algorithms can be vectorized and can be cleaned and removed all the errors, and you can use it. So there are multiple approaches or methods exist to capture spatial data. Once the data is captured, and it should be stored in an appropriate manner in order to utilize or like present it as a layer, or like do analysis or use it for decision making process and so on, for which the widely used approach is called database management system. So before discussing about how to capture attribute data, we will discuss about a database management system. In database management system, all the data will be stored as a tables like this, where you will find a rows and columns. So rows are entities or records of particular features. Say for example, a parcel or a county of one, like a particular feature, is recorded as a row. So each here row represent some like entities or like spatial features, you can say. And to describe these spatial features, and you can add attributes in terms of columns. Sometimes we call it as field technically, where each row will be described in a different like columns with the different fields. And of course, although we have many fields, at least one field should have some unique ID to represent each field, that we call it as a key field. The key field is very, very important to store your data without any duplicate. So that's why in GIS, whenever you capture any spatial data, system by default add a key field, a unique ID for each row, so that there won't be any duplications in your storage. So once you have a proper like a table with the rows and columns with the unique key field, and you can able to relate more and more data with your spatial information using an approach called relational database management system. Here, say for example, the first table contains some parcels and its values in terms of block, but it don't have a district information or city information or tract information or some other information. Whereas in another table where I could found geography of this like parcels, which means the district information, city information, block information, tract information, and other informations. So if I want to maximize or if I want to add these information to this table, instead of typing one by one, rather I can able to relate it using the common like identifier, or we call it as a unique field. So for example, here the block have unique field and the same block also available in another table with the same unique field. So using this key, unique like a field, we call it as a foreign key, you can relate both the data easily, or you can join both the data easily. So this is how you can able to capture attribute information for your spatial data. While digitizing, while creating spatial data, you no need to add all the attributes, rather just you can specify the entities, whether point or line or polygon, then create one common attribute field with a unique ID. Then all other data you can process it separately using Excel sheet or some other, and you can maintain the same unique ID, and both the data you can able to relate and capture it. Again, I'm just repeating the process. Say for example, I captured 5 points with the help of coordinate information. I captured coordinate information using GPS or some other instruments. I have coordinate information using which you can create the locations of these coordinates in GIS, and you can assign a unique ID for all these 5 features. Then later you can prepare information in the form of table with the same unique ID, then you can combine together. So the GIS using this relational database management system to integrate all spatial information and coordinate information. So understanding this relational database management system is very, very important to work with the vector model. Of course, raster also apply the similar approach, but vector uses more amount of attribute information, more amount of like data sets, which can be integrated or which can be managed better if you know the concepts better about relational database management system. So using this approach, we can integrate a voluminous of external data with the GIS database. Say for example, these are all the information I captured using a GIS software, and rest of the data I can capture with the other database software, even Excel sheet. And using unique identifier, you can integrate or join all the data together and form a complete database for various analysis. In similar manner, you can also integrate or link or join GIS database with external database or external database management system. So where your shape information or geometry information all can be converted into a database and you can integrate it. Say for example, here the spatial information is converted into external spatial database where you can hold it in a server or hold it in general application software, and you can do analysis or you can do GIS based decision support system. So this is how many of the databases, map databases, spatial databases are working. So whatever you are seeing, either it can be a Google map or Bing map or some other map or even Uber app, all employs similar approach where the spatial informations and other informations are integrated using georelational database management system. While discussing relating data, we commonly use two words. One is called joining, another one is called relating, depend upon what kind of relationship exists. Say for example, if one feature want to join with other feature, or you want to connect one to one, then you can use join operation. Directly you can join it because the same number of feature you are going to join it. However, sometimes you have a very limited information, but your database have more amount of information or many rows. Okay. So here you have one row. The same row is represented in your database multiple times. Say for example, this is on January 5th, this is on February 5th, like for every month you have data, but whereas it has only one spatial information. So in such case, which one I'm going to join with this one? It's very difficult. So this information should be related with multiple information. So here you can't directly join it, rather you can relate it. So this database and this database can be related each other. Likewise, sometimes you have multiple features, but the data, external data you want to integrate may have a very limited information. And that too, it is like unclear whether it is associated with this or this. So in that case, instead of like joining this data with this data, rather this data you can join with this one. This is called many to one relationship. So you can like externally join and you can do analysis. Like we can also encounter, we may also encounter a many to many relationship where you have many information and the database you want to integrate also have many information. So such kind of complex data can also be managed with many to many approach. So either you can use relate or join, depend upon the data properties or the data like relationships. So once you captured spatial data and joined your attribute data, then your data is ready for a decision support system or manipulation or some other analysis. But before, you have to ensure whether your data is accurate or not, for which ensuring data quality is very important. So you know that GIS is being increasingly used for decision support system, and most of the data sources are generated from multiple sources and integrated each other. In that case, ensuring data quality is very, very important, because if data quality is very low and whatever decision taken based on those databases are potentially severe. So for which understanding and ensuring data quality is very, very important. While discussing data quality, technically we use two terms called accuracy and precision. So accuracy, it refers to the extent that both attribute and the spatial information, XY information, corresponding with the real world counterparts. Whereas precision refers to the exactness of the data or precision of the data, how precise it is. So for example, in this case, the data is close to precision, but it's not, sorry, in this case, the data is like accurate to the center, but it's not precision each time you enter or like a hit with the different locations. Here the data is highly precise. All the data you entered are like related to each other. The uncertainty is very less, but it is not accurate. It should be here. And this is the right data set with proper data quality where you have a precision as well as accuracy. So GIS databases should have both this accuracy and precision, without which if you take any decision or if you do any analysis and it may not be accurate. While discussing accuracy, then two types of accuracy are very important. One is positional accuracy and another one is attribute accuracy. Positional accuracy often affected by human errors, because most of the case human converting it either using a digitized approach or automatic approach. We are digitizing, say for example, this is the original boundary and this is the way a person digitized the data. So using which if you calculate area or some other thing, definitely it may not represent the reality. So ensuring a positional accuracy is very important. Randomly you have to check and you have to like ensure it, depend upon the scale what you have used. And also, especially if you are using a vector approach and capture multiple amount of information for an area, then it is very important to check the topological error. Say for example, two polygons are digitized nearby. So in between, if you have a gap and this gap lead to some misrepresentation as well as area miscalculations and so on. Say for example, the counties are digitized, the county number 2 is digitized twice and entered in a duplicate, then it will lead to a problem while joining the data to which we will going to join with the two, whether this or this. So you have to ensure it whether it is properly mentioned or not. Likewise, if you are joining two lines, especially this is very important for network analysis. If you are capturing all the stream network or road network, it should be properly joined. So there are many topological error may happen while creating a spatial database that need to be identified and ensured and rectified to maintain good positional accuracy. Similarly, the attribute accuracy also need to be ensured, and especially if you are applying the numerical data. So for example, you are entering a numerical data, you have to enter properly all the numerical data with the proper row records. If you mismatch it, then it will lead to some misrepresentation. Likewise, we discussed about numerical data can be represented either integer or fraction. So while designing your database, instead of float or instead of fractional, you designed as a whole number. Then later you are entering the fractional information to the database, it won't accept or it won't like record it. So for example, in a column I created for a whole number, but I'm entering a temperature with the fractional values and it won't record it properly. And some data required a logical consistency also. And some of the data need to have a completeness in order to do some statistical calculation. If you even omit one or two rows or one or two columns, which will lead to some calculation error or statistical modeling errors. And these attributes in some of the case may used to represent as a labels over the map. So you have to add properly the labels about the different features, and accordingly we can able to represent it accurately on the map. So the accuracy of labeling, accuracy of entering labeling information into the database are also important while ensuring data quality. Sometimes for special data sets, you need to maintain temporal accuracy also. Say for example, the same data you are repeating or entering with the different time periods, then you have to maintain it, the proper time measurements, proper unit and frequency of update and so on. So temporal consistency of different data sets, especially if you do land use like a change reduction or some other change reduction, even if you do some weather modeling of a different time period you are comparing, and temporal consistency is very very important. All these data sets can be effectively managed if we store in a combined manner, for which there is a special approach in GIS that we call it as geodatabase approach, where all kind of spatial information, either it can be point or line or polygon or raster or even tabular fields, can be put together into a single system like a common file folder systems, similar to a zipped files, where you can like contain all the data in a single source, or single location, and you can able to efficiently manage it. That approach we call it as a geodatabase approach. It has advantages because this approach can able to manage larger file sizes. Say for example, take Google Earth or Google Map. It has voluminous of data covering entire world. So all the data should be integrated properly in a single like a domain. Although it represents points separately, lines separately, polygons separately, and labels you have, then some other analytical informations. All need to be put in a single database so that it can be efficiently handled. So for which this geodatabase approach is very, very important. But one problem, especially at lower end, is this geodatabase need a dedicated software package or the proper understanding of handling the geodatabase. So the skills and softwares are very important to maintain this geodatabase. Once you prepared a geodatabase which contains all your spatial and attribute information and properly integrated, and you can use it for spatial analysis or spatial representation. Even you can share the information widely through websites or through your peer network, or even you can share the information with other spatial decision support system managers or other like group of peoples. So while sharing or publicly host the data or representing the data in a public domain, maintaining metadata is very important. So metadata is a way of describing an information resource so you can better understand the data. So using metadata, you can able to explain how this data has been generated, why this data has been generated, who has created, and what kind of sources have been used, what coordinate system it has, and what kind of scale it followed, and for what purpose this data made, and what are the limitations it has. So during which time period it digitized or captured or analyzed. So all informations we have to put together and we have to arrange in an order and we have to share along with the data. Then only the effectiveness of data fulfilled. So with this, I just stop it the theoretical aspects of data management for GIS. Now I will give you a short demonstration about the principles or theoretical aspects we discussed using our GIS software. Here I have two data. One is spatial data representing the districts of a country, and another one is yeah, attribute data, which is collected separately and representing COVID like a case information for all the district. When I look at the district data existing district data, I could found the population density where somewhere it's high, somewhere it's low, somewhere is moderate, and later I found some other source where I could find COVID data also. So I have interest to understand whether is there any direct relationship between population density and COVID cases, or so I am a health department guy and I want to understand where the cases are high, where the cases are low, so that in next outbreak, what kind of strategy I have to adapt, for which I want to like compare or spatially visualize the COVID information with this basic distribution of districts or basic demographic details. One way is you can take each district. Say for example, this is a district polygon. It has attributes. It has unique ID. You can see unique IDs, and it has many attributes. Each row representing some character. Okay. So some say for example total population, male population, female population, population density per square kilometer, district area, and so on. But it don't have any COVID information. The one way is you can create one more field and you can add the number of cases and you can visualize it. But it takes much time because in this database 640 districts are there, and adding all this data one by one, it's time consuming process. And of course, while entering those information, you will do some potential error or mistake as well. Instead, I want to integrate these COVID information with this data using the relational database management approach, because both the data have a unique field. Say for example here, if you look at the census code, all the 640 districts have been assigned unique value 1 to 3, and using which you can able to integrate. Say for example here also I found the census ID and it has the same 640 districts with the unique ID. So if you look at ID number 1, it is Kupwara, and this is here, then Badagam, this lake. Okay, so we have a data, two databases with one-to-one relationship with the unique ID. So using which you can integrate both the data together. So I just use an approach called joining because it has one-to-one relationship. And in this database, the census code has unique field or unique key, and the joining external database also have the same key under the name of census ID. So by using these two fields, I'm just validating and found that all the records are matching. Okay, except only one record, that is no data value. So in your district there is one boundary which don't have any data. So other than that, this exclude one, it has 640 districts. This is also have 640 information. So you have perfect one-to-one relationship, and I just join. So now the moment you like joined both the data, earlier this district has only limited information up to the district area, but now see you have the cases in wave 1, wave 2, total cases, death, and all other information related to COVID. So now both the databases are integrated together, so using which you can easily map it. Say for example, instead of population density, I want to identify the total cases. So where the cases are high, the cases are not exactly matched with the population density, whereas the cases are high in southern India rather than the northern India where the population density is high. So you can have a good insights by integrating these data together using database management system. So with this, I just stop it. I hope you understand the importance of database management system and various aspects of geodatabase management system, georelational database management system. Thank you.